All right, line V1, learning task 3, automatic and sequence types of controls. We've already covered most of the devices that we are going to go and use, the individual piloting devices. Now we're going to go and cover sequencing of controls. And this is a very common thing in industry where we need to go and have one thing moving before the next thing can start moving, before the next thing can start moving, etc. Generally speaking, it's going to be done to prevent mechanical issues. It's not so much for electrical issues, although in some cases, if we have got large enough motors, we will want to go and stagger the start times. If it doesn't make any difference, to us electrically or to us mechanically, sometimes we'll just stagger each of our individual motor start times because it's going to give us less disturbances on the actual lines themselves. Other times it's going to be purely a mechanical thing, as we're going to see later on when we take a look at this wood chip conveyor that's coming up inside of here. Let's go and take a look, though, at our very first one, which is going to be sequence control of 3 motors. And this is really just going to be one that feeds over to the next, that feeds over to the next. What we're going to see is that my M1 coil is going to go and start the M1, which is going to go and start the M2, which is then going to go and start my M3 and seal in my circuit over here. Let's follow this thing through. At rest right now, we would have energization up to this point, and up to this point over here. None of these would have complete circuits yet at this point, so we could not actually go and start this whole system up. The instant that we go and press start on our system, we will go and complete this line over here. As soon as we complete this line, that is going to go and energize all the way through to my M1, which can carry out to the line there. Provided that M1 energizes, then we are going to go and close in my M1 contact over there. Once that goes and energizes, that is going to go and energize M2. And then once M2 has gone and energized, that in turn is going to go and close the M2 contact in the next rung down over here, which is then going to go and operate my M3. And last of all, we're going to go and see that M3 is going to go and close in this set of contacts over here, which is going to go and provide my sealing contact. At that point, we can go and open up that push button, and all of these motors over here are going to be operational. It's going to be really fast. Click, 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 click. That's going to happen so fast that it's hardly going to go and make any, noticeable difference to any of us as we're actually looking at it. But it is going to be long enough that we have to hold our finger on that push button, the start push button, for, just a second or so, just long enough that we're guaranteed we're going to have that engagement across each of these coils. As far as taking this thing out, anything that is going to go and operate our stop will go and shut this thing down. So if I were to go and take the stop over here and shut that down, that in turn is going to go and shut down M1, which in turn is going to go and shut down M2, which in turn is going to go and shut down M3, which in turn is going to go and lose my sealant contact over here. We're back to this whole setup being, sitting at its at-rest type of position. I do want to note as well that if we get this whole thing started up, and I'm just going to go and energize M1, which is going to go and close that, energizing my M2, which is going to close that, energizing my M3, which is going to go and seal me in. Let's draw all these seal-ins over here. That this one does have a little bit of an inherent drawback. And that inherent drawback is if these are designed to go and operate together as a group, if I lose overloads on one of them, I don't care which one would lose overloads, but let's lose overloads off of this one over here. I'm going to go and if I lose that overload, it is going to go and shut down my M2. Once it goes and shuts down my M2, it is going to go and shut down this one over here, which is going to be my M3, which is going to go and shut down this one over here, which is going to be my M1. And it's not really a big deal the way that this happened, other than the fact that if it was a timed sequence that we had where we had to have one on and then the next one and then the next one, that would cause problems if we had to go in the same sequence to go and turn stuff off. Because in this case, whichever one goes out on overload first is going to be the first one to shut off. It's going to cascade that one on to the next one, which is then going to cascade us on to the last one. Like I said, though, probably not an issue for a lot of, the applications that we're going to be using them. If it would be an issue, though, that's going to be up to you to create a more complicated set of controls where you're going to go and shut them all down simultaneously. My suggestion at that point would be to move all of the overloads. If you did have to go and shut them all down together, take the overloads for this motor, the overload contact for this motor. I would move all of them up into the same line that we are going to have up top here. On the topic of overloads as well, I do want to note that right now inside of here, we've been looking at line 1 and line 2. And that's fine for us to have an overload over here when we're dealing with line 1 and line 2. However, that is going to change if we were to go and take a look at a single phase device. Let's take a look at what the Canadian Electrical Code has to say on this. There are some very specific rules inside of the Canadian Electrical Code to deal with safety. And one of the big things with motors and motor controls is operational safety when we are dealing with a grounded type of system. 28506, grounded control circuit. Go to your code book, highlight as we go through here, because there is some very, very, very important things that we need to go and see inside of here. 28506 says when power for a control circuit for a motor controller is obtained conductively from a grounded system, the control circuit shall be arranged so that an accidental ground in the wiring from the controller to any remote or signal device will not A, start the motor, or B, prevent the stopping of the motor by the normal operation of any control or safety device in the control circuit. Let's go through that in detail. In detail, it says here where power for a control circuit. Okay, so what they're talking about, control circuit power, is obtained conductively from a grounded system. So anytime that we've got a system that has got one lead grounded, the most common one for us is going to be a 120-240 type of system, a single phase type of system, where we have got that grounded neutral, or a 208-120 three-phase system, where once again we've got that grounded neutral. If I'm using 120 volt coils, I got to be real careful with this rule, because this rule is going to go and tell me some special stuff. The other place that we sometimes see grounded controls is if I've got a DC system where the negative has been grounded. This sometimes happens, or when I've got a low voltage AC system, 24 volts AC, where I have grounded down one side of that 24 volts. As long as there is a ground that is attached some point in that circuit, it is considered to be a ground. So always know what system you're going to be taking your control from, then follow this rule. So you should have this highlighted, obtained conductively from a grounded system. This control circuit shall be arrived so that an accidental ground will not. So I have accidental ground highlighted and will not. That's all you need. Accidental ground will not start the motor. And that would be bad if, there was a ground fault and all of a sudden motors, boom, fire up and stuff. Or prevent the stopping of the motor. By preventing the stopping of the motor, what they're talking about specifically are going to go and be my overloads. Let's just take a real quick look at just the top rung here right now before we go back into what we need to cover here. But this is going to be, necessary stuff for us to cover, so we might as well hit it while we're over here right now. Let's go and take a look at this. We're going to say that this was my neutral. Okay, so this was a neutral over here. There would be an issue in this overload. Now, what is this overload? This is a set of contacts that is coming from the actual overload heaters themselves that are going to be placed in line with the motor conductors, right? Motor amperage is going to flow through the overload heaters. If the heaters get hot enough, they're supposed to go and trip out this contact over here. It says that under our code, a accidental ground shall not prevent the stopping of the motor. And if we go back to this one over here, we can see that if I had an accidental ground over here between the motor contactor and the overload, I also know that my neutral has got a purposeful ground that we are going to go and have on our neutral. And right now, what I could have happen is if I had operation, where I had this sealed in and it was running like that, if this were to go and open, but I had that accidental ground between the contactor and the overload, what could actually happen is I can go and deliver over top of my bonding system back to the neutral like that, and I've still got a complete circuit at that point, which means that this thing is not going to shut down, even though that overload, which is defined as this, a regular controller safety device, even though that overload has gone and activated, it is going to be problematic. So, talking about overloads here, since we're kind of in situation with this one here, when we have got a 120 volt circuit, and we're going to see some mistakes probably throughout some of the materials, whether it's going to be inside of practice materials or whether inside of the binder, anytime that I've got a neutral, I do need to go and take my overloads and I need to move my overloads to the front. The most common spot to go and place those overloads is going to be right over here ahead of that stop. At that point, if I had a ground that were to go and happen, because I would have removed the overload from here, that. Pretend like that's a line all the way through there. Any sort of a ground on the system at that point would not continue to cause this thing to run, right? Obviously, if I ground here, I mean, it's the exact same thing as having my neutral grounded over here. If I had a ground over here, that's just going to go and short circuit this one because I got no load in there anymore, and it's going to go and kick this thing out. We're back to being safe. So single phase, 120 volts. If you get into motor control, make sure you move it there. 120 208. If you have a 120 volt control circuit, make sure you move the overload over there as well. 347, any of the 277, 480, anything like that. If it is conductively taken, so directly wired onto a system that has a neutral, you have to move the overloads to the front. Okay, going back now to the circuit that we were talking about, or this whole concept of sequence control. This over here is going to be my ladder diagram that I'm going to go and have. What I do for my ladder diagram is I then transfer that one into a wiring diagram. And the wiring diagram that they're showing over here is for a standard set of contacts. Now let's go and break this thing into just a couple of blocks, okay? Each one of these blocks is ideally going to be the same thing. If I were to look at it for the power side of the circuit, and we'll come to the control after, power side of the circuits, I would have my line 1 that would be going through its overloads and then going down to the motor. I would have my line 2 that would also be going through its contacts, down through its overloads, and then to the motor, and I would have my line 3. Same, I should stick it through its contacts, going through its contacts, and then down through the overloads and to the motor. It's going through the actual overload heaters on each of these, not through the overload set of contacts. So we're just monitoring the lines itself. This is going to be the power part of my wiring diagram. The control part of my wiring diagram is going to be all the rest of the components that we are going to have over here. Control diagram is going to be based off of, and I'm just going to erase, no, actually I'm going to erase these lines over here, but I'm going to go and run the rest of this one over here. A couple of components that are going to be for my control diagram. First one over here, they're kind of hidden it behind here, but that's the actual motor coil itself. It's not making contact with my line 2. They're just showing that one behind there. This is going to be the actual contactor that fires these contacts up top over here. We see that we've also got this little setup over here, which is going to go and be my actual overload set of contacts. And I see that that overload set of contacts is going to be in line with a contactor itself. And I'm going to go and see that the other component that I have inside of here is I'm going to go and have a normally open set of contacts over here that are going to be coming from a different coil. Now this diagram over here shows contacts, 3s and 2s, that are coming from the sames on the coil. So there's a little bit of a, it's a bit difficult to see it off of this. Easiest thing for us to do is just to trace over top of these with a highlighter. So I'm going to remove a bunch of these components over here right now that are kind of traced over top of when we will go to a individual highlighter for each one of these motor connections. We'll start with the motor number 1, which was going to be this top one over here because it's got the bulk of our control components inside of it. I will be feeding in on my line 1. I go directly through my stop and then I get up to my start. So I'm going to have fed in on line 1, gone directly through my stop, directly up to the start. That's as far as we've gotten. From the start, I'm also going to go and have to feed over to my set of contacts, my sealant set of contacts. And if I look at my sealant contacts, I see it's the sealant contacts that are going to be the auxiliary contacts attached to my M3 motor. So I'm going to go to this one here, and wrong one here. So I'm going to go to this one here, and I'm going to go and take my auxiliary contacts over here off of the M3 motor. So now I'm up to one side of the contacts. I go back to this one over here, and then I see that the opposite side of my start switch ties back to the M3 contacts as well. So let's go and do that. The opposite side of my start switch over here is going to go and tie back to my M3 contacts as well. Now they're showing it as a bit of a long run to get around it. They made a junction on the side of this coil over here. And that coil that we're seeing that it's making a junction on is actually this over here. So on the control circuit, if you can imagine it, it's like they're going from the M there and then back up like that. It's not shown as a T, it's just shown as, they're making both those connections on that same one. So we're up to our M1 over there. We see that we're up to our M1, our actual coil. From our coil, we then just go through the coil to the actual overload. for the same motor, right? We want to have the overload attached to the same motor. So we're going to go from here, we're going to go through the coil to the overload contacts. Same deal, it's not the heaters, we're just looking at the contacts. And then from the contacts, I'm going to go up to my line number 2. And everything after that is a lot more simple to go and follow through, because all we're doing past this is now we are just going to go and run from my line to a set of contacts to the contactor and overloads and out to the other line. We'll follow that on motor number 2. We're going to go from my line. We're going to go and take its contacts off of the M1, and then it is going to go and feed all the way down here to its own coil, through its coil to its overloads and back to its line 2. And we would see the same thing that it's going to be off of my number 3 over here, motor 3. Make sure that you can go and do these type of analysis, that you can match, different wiring diagrams with different sequence controls that we are going to go and have inside of there. Okay, let's talk about time sequence. The first one, there was no timing in between. In some cases, we do want to go and put that timing in, because then it's going to go and either allow something to come up to speed, or it's going to allow us to go and just eliminate inrush, because we have these big motors that are going to go and start. So what we will do is we will go and put in a on-delay timer. Our control circuit for this one, once again, shows that, look, if we press the start push button, we got power up to here normally. So as we press the start push button, it is going to go and energize M1, which is going to go and seal itself in. At the same time as it energizes M1, it is going to go and start up my timing relay, which is then going to start timing dot, 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 counts 5 seconds, and at the end of the 5 seconds, it is going to go and close this, which is then going to go and operate my motor number 2 off of here. It gives us motor 1 starting, and then a pause, and then motor 2 that is going to go and start. The danger with this one over here, once again, is just going to be in where the overloads are placed, if they are going to be causing problems. If I were to lose my overloads over here, if the motor 2 was to get too hot, motor 2 would just go and shut off. It would not shut off motor 1. So if motor 1 was feeding onto motor 2 or something, you got to set up belts or something like that, you wouldn't want to have that, because as soon as this one shuts down, this one's just going to keep piling crud on top of that thing. If they did both have to shut down at the same time, what we would want to do is we want to take that overload and we would want to go and put the overload in series. Over here, it's fine to be on the tail end of our contactor, because we see that we are doing line-to-line types of control. But once again, if it was neutral, if this thing had a neutral over here, what we would be doing is we'd be moving this overload to the front, as well as we'd be moving this overload to the front in series with it as well. There's another timing diagram for this one. This one over here is using a timing relay, by the way. That is one of our pneumatic or one of our hydraulic type of timers there. Those are ones where we provide power to the coil, and then it either has to force air or it has to go and force, some type of silicone fluid to go and operate. We, at this point, don't see a ton of this stuff. What we usually will end up seeing is we are going to go and see electronic timers. And those electronic timers are just going to go and take in a signal. If you watched the previous video, you should be able to explain exactly what a signal is and what on-delay timers and off-delay timers are all going to be about. And as well as, I guess, just what the actual timing diagrams are going to go and be about. If we take a look at this one over here, if I want to convert this one into a digital type of timer, what I would need to do is I would need to go and have my timing relay coil that is going to go and get energized, as well as I'm going to need to go and have my timing relay signal. Now, for an on-delay set of timing like this, usually what that's going to mean is that I'm going to go and have another signal that I'm going to go and put on, because most of my timing relays, I can go and power them up at the same time as applying a signal, and then they're going to start to do their timing, and when they operate, then they're going to go and give me my operation. Usually what this is going to go and look like is that somewhere on that octal base, if it is an octal relay, that's an 8-pin relay. If we had something that looked like that with the octal base, what we will have is then that's usually we're going to go and have 2 of these that are going to go and be my coil, my power, and then usually one of these that's going to go and be my signal. Usually it seems to be this one that sits around here on the side over there, number 3. Usually we're just going to end up having a short from here to here, going from the one side, the positive side of my timing relay. If it is going to be DC bias, I'm going to go and short those 2 together. Once again, just follow your manufacturer's documentation in it. But know that if it is going to be a digital timer, you also have to apply power in most cases to the actual signal terminal. Expect to see more digital than pneumatic and hydraulic in you guys' lives. Okay, off-delay timers. Off-delay timers are a common part of motor control as well, and an off-delay timer is going to be more complicated with the electronic end of it. The reason that we use a lot of off-delay timers is usually where we have got a cascaded type of system, where we're feeding from one component over to another type of component. I'm just going to go over here to this thing that they're showing, where they've got three types of conveyors over here that are, carrying wood chips to wood chips to wood chips. We carry them uphill, spill them down, carry them uphill, spill them down. We can go and move materials around a yard relatively easily. We're going to examine this one later on. But if I were to go and press my stop, what I would want to go and happen is I wouldn't want all of this to shut down necessarily instantly. If it was an emergency, absolutely. We hit the E-stop, that should shut everything down instantly. But if it was just a regular stop, I don't want to go and shut everything down. What I want to have happen is I want this thing to continue running. Let's say that a revolution of each of these takes 30 seconds. Okay, it takes 30 seconds. What I would need to do in this case is I would need to go and have off delay timers. So that as soon as I hit stop, there's going to be a 30-second delay, and then motor 3 is going to go and shut off. And there's going to have been a 60-second delay, and then motor 2 would have shut off, and there would have been a 90-second delay before motor 1 would go and shut off. That way, the first 30 seconds, after the first 30 seconds, this one shuts off, and it will have already emptied all of its wood chips onto this one. At 60 seconds, which is the 30 seconds for this one to clean out, plus 30 for this one to clean out, this one would shut off because it would be clean. And then at 90 seconds, this one would shut off because it would have had the 30 seconds for each of these other belts to go and clear out. Generally speaking, you're going to hear about clean out timers, more so than, use an off delay off of it. You'll just have people that'll say, oh, you need to have a clean out timer on that so that we can go and move stuff. There's a lot of materials that will move really, really well when they're already in motion. But, once that object goes to rest, it gets really hard. And so having a loaded conveyor, if you don't clean out a loaded conveyor or augers or things like that, what can happen is if you shut it down full, that you're actually going to have to go and dig this whole thing out because it can't start underneath load. So, yeah, we're going to go and call that off delay. We're going to call that thing clean out timers. And let's go and take a look at what that looks like. Oop, that's my on delay. Let's take a look at this one over here. This is going to be my off delay timer over here, and it is going to go and have a normally open timed to reopen, which means that instantly when I go and apply power, it's going to close, and then once this thing shuts off, it's going to wait before it goes and opens up. So if we were to go and operate this, let's just step through. What we're going to go and see happening is we press the start button over here. Once we press the start button over here, motor 1 is going to go and energize. Instantly, it also energizes timing relay 1, and it seals itself in over here. Because it operated the timing relay, this is a normally open time to open, which means it's instant on energization. So instantly, this one goes and closes in, and my motor number 2 also is going to be energized and running. When it comes time to go and stop, what I'll do is I will go and hit my stop button over here. This is a regular stop, not an emergency. When I stop that, it is going to go and take out motor 1, and it's going to take out the timing relay. But the timing relay itself does not release this until 5 seconds after it has lost power. So this motor shuts off, but there's still a timing, tick, 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 tick. 5 seconds later, boom, this one is going to go and open up, and it's going to go and shut down this motor. You should be able to go and develop a timing diagram for this type of a setup. I'll just quickly draw one out here with you guys. The first thing that we would go and take a look at is we would take a look at the conditions of our stop and of our start. So I'm going to go and start with stop, start, and then we're going to go and call this thing M1/TR, and then we're going to call this one here M2. And so as long as my stop is going to go and be high, so we're going to start with just a high stop, we'll come back to that one in a minute. When I press my start, the instant that I go and press my start, I'm going to go and see my M1 that is going to come on instantly as well as my M2 that's going to come on instantly as well, right? Because M1, when it powers up this as well, and this instantly is going to go and close. So I see that all three of these are going to go high at the same time. Then I see that when I take my stop from being high and I take my stop low, I shut that thing down, what's going to go and happen, so I'm just pressed my start over here. I'm just going to drop my start now because I don't need to keep the start high. Shows just a button press on that. So I press my stop. As soon as I press my stop, I'm going to go and see that instantly motor 1 and timing relay 1 are going to go and get shut off, and that instantly I'm also going to go and start a time, right? T, like that. And then that my motor number 2 is going to go and shut off based on that time being completed, my 5-second time that I have over there. Just shows me my operation that boom, both of these turn on at the same time, and then when I press my stop over here, that this set shuts off, this one stays on for a little bit longer. These are technical documentation that you're going to be expected to go and read and understand and produce in some cases on job sites as well. This one over here, we could do a timing diagram for as well. Let's go and quickly, no, we'll come back to this one here in a minute. Let's finish this one up first over here, the off delay. I did tell you that for an off delay type of situation, it is a little bit harder for us to go and do these with the electronic timer, and that's because we do still need to maintain power on the timer coil to go and operate these. So if I'm using electronic timers, what I'm usually going to go and have is a circuit that's going to go and look like this. I'm just going to wait that out over there. And I'm going to go and have a set of contacts, and input over here, and I'm just going to call this thing my signal, TR signal, that I'm going to go and have going in. And I'm going to have as well underneath here, in parallel with this, I'm going to go and have a constantly powered timing relay. It's going to look like that. So the timing relay coil itself in an electronic timing relay stays powered on at all times. It is the signal input that just acts like the old school timing relays, but it's just going to be the one that's going to monitor. So if I were to follow my operation with a modern electronic one, what I would see is I'd press my start, I'd energize M1 at the same time, I would be providing signal into my timing relay, which would then go and start that thing up. Really, I could just add, for this one here, I could just add in another line that I'm just going to go and call signal, because that's all it is. It's just coming in as a signal. I'm going to see that signal goes high, and then when that signal goes low, that's when my timing would actually start. We'll move that T down here to this one as well, just to show that that's where the timing action is happening off of that signal line over there. Just remember, with any electronic ones, that the coil of the electronic timer in most cases needs to stay energized. Let's go back up to this one over here. We're going to just quickly develop a timing diagram for it as well. We know that this is a normally open time to close timing relay, which means that I'm going to have a delay on my M2 operating. So I'm going to go with the same. I'm going to start with my stop high. I'll write them all out first. Stop, start, and then I'm going to go and have my M1, and then I'm going to go and have my M2 over here as well. So I'm going to start with my stop being high, and we'll just keep that stop kind of high all the way along the top there. I'm going to have my start. That's going to start low over here, and when I bring my start push button high, what it's going to do is it's going to go and energize M1/TR. We'll just call that /TR as well. So I'm going to go with my M1/TR. That's going to go instantly high, and it's going to stay high even after I take my finger off the start push button, because it's going to have sealed in over there. And it is going to go and start running. And as soon as I initiate the timing relay, I'm going to go and start that timing, right? That 5-second timing. We'll do that across here. And then that 5-second timing is going to go and give me my delay. That is then going to go and start up my M2. So we should go and see that we have got, once again, this timing that has given us that delay on our M2 starting up. At that point, we would have both M1 and TR running. As soon as I take my stop low, then it is going to go and take M1 low instantly, as well as it's going to go and take my M2 low instantly. This would be a proper, valid timing diagram that we would use for one of these with an on delay. It shows us that delay, that everything is always read from left to right. As long as my stop is high, I press a start. As soon as I press the start, I can see that that start is going to go in effect. My M1, turn it on, it starts my timing. And after my timing has, ended, then it's going to go and turn on my M2. And when I hit my stop, it all shuts off like that. Understand how to go and read these diagrams. Practice making some of these diagrams as well. Okay, moving on. Let's then go and talk about actually, no. We're going to stop right over there on this one here because that just kind of gives us sequence control through time sequence control. We'll stop the video because it's in a half hour, and then we'll start the next ones here, the anti-plugging, with another video, just so it doesn't turn into too long of a video if you're trying to find these later on when you're studying, because you all study so hard off of these videos all the time instead of just watching them for like 12 minutes average, as YouTube tries to tell me. All right, that's it.